me. I'm going to keep my talk mostly motivational and not emphasize the formulas. I mean, not so much emphasize, but I'm going to try and sweep some things under the rug. And if you want to see what's under that rug, then feel free to ask me at the end of the talk. But I won't force that upon anyone if they don't want to see details. So I'll keep it mostly about the motivation. So the talk is called quantum loop groups for symmetric Cartan matrices. And let me sketch the main idea of what I'm going to do. As a diagram, the main idea of this talk and of this project in general is to consider a Lie algebra G. And to recall that in representation theory and in quantum algebra, we can apply two procedures to this Lie algebra G. One of them is quantization. So we can replace the universal enveloping of the Lie algebra Z by its quantization, which is going to be just a quantum group UG of G. So what I call the quantum group is more appropriately called the quantized enveloping algebra, but I will just call this one. So this is a well-known object, how we define it, but just for the point of motivation, I think that this is shows the objects that we are going to consider. The other operation we can do here is to replace G by its loop Lie algebra. So the loop Lie algebra, which I will also define a bit later, as a vector space is just G-valued polynomials in one variable T, or round polynomials actually, since I want this to be e to the plus or minus 1, and this Lie algebra can also be quantized in a way which I will explain. And the corresponding object over here will naturally be called UQLG. And just looking at this square, the way you go from here to here, it is called nowadays quantum optimization, and you can think of the vertical procedure over here as being like an analog of this. So here's what I want to do in this talk. I claim that from a certain point of view, which I will explain, this object is well understood, this object is well understood, and this object is well understood, but not this one. And the goal of this talk will be to understand this object out here. So let me actually write this goal. Talk is to understand UQ of LG. Now, just for some historical context, in the sense that
sorry, just a detailed question. You omitted to speak about the central charge, the central extension, because to cut things short, or because there's some existential reason
why? Cut things short. I mean, you can add the central charge in there with no problem whatsoever, but I don't want to go through
yeah.
So really, you can think of this as the optimization, meaning G hat instead of LG, but it's really no benefit from my point of view. So I'm just going to keep things simple. All right. So the goal of the talk is to understand UQLG. And actually, the goal of the talk is to define it. Because as I will try to argue, this thing was defined. So this was done, this was understood by Greenfeld like 35 years ago or something. But only in the case when G is of finite type. So when G is finite, it's a finite dimensional algebra over G. The goal of my talk is to do this when G is more generally a Casimir algebra. So we'll do it. We'll do this for G, a Casimir algebra. So that will be the goal of the talk. To do for G Casimir, what Greenfeld did in the finite case all those years ago. But unfortunately, it's not that simple. It's actually going to turn out that new formulas and new features will appear. So I'll show you a big formula at the end, which is new. And if you want to see some more formulas, then you have to let me know and ask me after talk because this is one of those things which I'm going to speak on the road. All right, so this is the plan. And to motivate things even further, I'm going to start from R2B, the simplest finite dimensional Lie algebra over C. Let's say G is equal to SLN. And let me show you the point I'm trying to make for SLN, and then we'll go and generalize from G to UQG to LG and then to UQLG. So G is equal to SLN. We all know what this is. This is the vector space of traceless and binet matrices, and it's made into a Lie algebra by the commutator. So x comma y is xy minus yx. We'll probably love this. The nice thing about this Lie algebra is that we can actually present it explicitly. So as a vector space, it is the sum over all indices I different from j of Eij, well, the multiples of Eij. So here Eij denotes the elementary symmetric matrix with a single one on row I and column j. And then you also have to put the diagonal ones. But here you only go from k to n minus 1. And here you do C of ekk minus ek plus 1k plus 1. You see, I'm not going to dwell on this because everybody in the audience knows this. So this is what G is explicitly. But what I actually care about is what is G as a Lie algebra. So as a Lie algebra, you actually don't need all of these basis vectors. You don't need all of these Eij's. What you do need is to say that G is generated by just some of them. So it is generated by the following particular instances of these elements. And the standard thing for people to take here is to take EI, which is EI plus 1, FI, which is EI plus 1I, and HI, which is EII minus EI plus 1, I plus 1. All right, so G is generated by these things, modulo relations. So let me tell you what the relations are. And if you think that I'm going to list all the relations, then this is exactly the kind of thing I don't want to do in this talk. So I'll just tell you what the most interesting relation is for me. The most interesting relation is what people call the SLN relation. So in the particular case of SLN, it's the particular commutation relation between E's. So the commutator of EI and J is equal to 0 if I and J are far apart, meaning that their difference is bigger than 1. And otherwise, you have this slightly more complicated commutator, so E plus or minus 1. So the double E bracket for all I. And actually, the complete set of relations is this thing, etc. So let me tell you what etc. means, because we're going to see it over and over in this talk. So I might as well just tell you what it means, or what I want etc. to be. So throughout this talk, etc. means plus the analogous relations with E is replaced by F, with E replaced by F. Is this part of what visible here?
Yeah.
And some straightforward and pretty standard in the theory of quantum groups, some straightforward commutation relations between E's, F's, and H's. So whenever you see me write etc., I just mean, these are the key relations. Everything else is just like a standard commutation relation of E with H, F with H, and E with F. All right. That's what I want to do in general. So let's talk about Hasmul algebras for a second. Are there any questions about the example of SLN? I put it up there, and I know that people at home have glare over there, but I feel like the glare is on the definition of SLN, so maybe it's not so much. All right, let's let's define Hasmoodi algebras. So first of all, I have to define for you what a Cartan matrix is. So a generalized, I'm gonna write down the keywords here, the generalized symmetrizable Cartan matrix is a matrix of integers whose rows and columns are parameterized by the same finite set I. So I'm just going to write this such that the aij's take the following form: 2dij divided by dii, where the dij's are now integers, such that the diagonal ones, the dii's, are even positive integers, and the dij's are symmetric. These are equal to dji, and these are that's what I want to say, and these are non-positive integers. So the point is that these dij's are positive and even on the diagonal, non-positive on the off diagonal, and the Cartan matrix is given by this thing. Now the condition that this ratio here be an integer is quite a strong condition on the Cartan matrix. Okay, so what we do with such a Cartan matrix? Well, to it we associate the Hasmoodi and the algebra. So the Hasmoodi the algebra associated to a Cartan matrix C is the following. Let's call it G, even though I should have introduced C in the notation for G, but I'm just going to call it G because the Cartan matrix is arbitrary for the time being. So this is G, which is generated as a Lie algebra by symbols EI, HI, and FI, where I goes over the exact same indexing set as the rows and columns of the Cartan matrix, modulo the following relations. And as before, I will just give you the relations which I care about the most, and then just say etc. The relation which I care about the most is this one. The iterated commutator of EI's with a single EJ here, and the number of Lie brackets here is 1 minus Aij, the entry of the Cartan matrix. This thing has to be 0. So this is not very legible, but you know that this means Lie bracket. This thing has to be equal to 0 for all I different from J. So when I is different from J, the number Aij is 0 minus 1 minus 2 dot dot dot. So the number of Lie brackets is 1, 2, 3 dot dot dot. So you know the Cartan matrix encodes the number of Lie brackets which you put in this commutator, and then I need to take my pink color and write etc. here, because then you have to also put in the analogous relation for F, and you have to put in the standard computation relations between E's, F's, and H's. Well, the standard example here, we've already seen it. So SLN, the Lie algebra which you have on the top board over there, it corresponds to the Cartan matrix given by 2, 2, 2 on the diagonal, minus 1s on the off diagonal above and below, and 0s everywhere else. And this is actually a particular example of a symmetric Cartan matrix. So I'm going to write it here is, oh no, blue is not ready at all. I need some. This is a symmetric Cartan matrix, which means none other than the condition that dii is equal to 2 for all I now. So we encounter this notion in. Any questions about this? The definition of a Cartan matrix and of a custom D algebra, and about why it generalizes the example of SLN. I can imagine that this is known to lots of people in the seminars, so I don't want to keep pestering you for questions if there are none.
I guess I have a question.
So,
Are the D's part of the structure, or are they property? Like,
a structure, I would say.
so because you could also just here you could choose D's. Yeah.
So usually people say that you assume the GCD of all the PIIs is 2, but all of the results I'm going to say are kind of invariant under the scaling of all of these D's, so it doesn't really matter. So for our purpose, let's take the D's as part of the data.
Okay.
Because you will see all of the formulas will kind of be in terms of these anyway, so we might as well make them part of the data. Cool. So that's what SLN is. Let me say something about why one would care about Cartan-DB algebras. So examples of Cartan-DB algebras include, as you can imagine, all the finite dimensional D algebras. So a simple finite dimensional D algebras correspond to so-called Cartan matrices of finite type, which are positive definite. So include finite dimensional D algebras over C. Everything is over C. I don't want to have any complications here. Also, affine D algebras. Some people are really into classifying a wider class of D algebras called hyperbolic D algebras, where there's lots of interesting combinatorics and representation theory in that. But instead of giving you more and more examples of this, I will tell you an interesting generalization of these. Cartan-DB algebras can be generalized further to Borcher's D algebras. So they are a step in the direction of Borcher's D algebras, which are also extremely important in math. And I can tell you why. Can be generalized further Borcher's e.g. the famous monster D algebra, which was used in the proof of the Monster-Wolfsheim conjectures. So you see, there's quite a lot of incentive to study all of these D algebras, and I think a setting of Cartan-DB algebras is really important, especially in geometric representation theory. All right, so I've talked for like 20 minutes, I think, almost, because I think it's such a nice picture and it's worth giving all of these introductions. I've only talked about the top left corner of my diagram over there, and I want to talk about UQ of G now. So what should UQ of G be? So UQ of G should be other than a deformation of the universal enveloping algebra of G. So the universal enveloping algebra of G just means that instead of being generated by E's, H's, and F's as a Lie algebra, you're generated by E's, H's, and F as an algebra. We impose the same relations. Now UQ of G should be a deformation of that. So this should be generated by EI, HI, and FI, I and I, modulo some deformation, some Q deformation of the defining relations of a Lie algebra. So some Q deformation of this relation in yellow, that the commutator of EI, the commutator of EIJ is 0. Now here, deformation in the most basic possible sense means the structure constants of this Lie algebra are integers. You deform them by making the structure constants to be some rational functions in Q, which specialize to set integers when you set Q is equal to 1. But of course, then you have the problem that there are many ways to do this, and you don't just want to deform in a random way. There's lots of freedom. You want to deform in a way which preserves the structures of U of G. And the main structure you want to preserve, so to appropriately define this, your goal should be to preserve the Hopf algebra structure of UQ of G. And it will turn out that there's a unique sensible way of defining U of G to UQ of G in a way which keeps it a Hopf algebra. I could actually proceed here in two ways. I could either tell you what the Hopf algebra structure is, so define algebras and bi-algebras and mapping rules and so on. But I kind of feel like people would be not particularly interested in something which is actually nonsense. So instead of telling you what all of these things are, I will give you a recipe for ensuring that UQ of G preserves all of these structures. So here's how you. And I actually think I can erase this part over here because we really don't have to see G is equal to S. So how to make sure that you preserve the Hopf algebra structure? Well, let me give you one way to construct UQ of G. You start from U tilde plus Q of G. And this is just a boring thing. U tilde plus Q of G is just going to be the free associative algebra generated by the EIs. I have to put my IC of Q here because the structure constants are no longer numbers, they are polynomials or rational functions in Q, but whatever. So I'm starting from simply the algebra generated by EIs with no relations. I'm doing the same thing with UQ of minus G. I'm just calling the generators of the FI instead of EI. So far, nothing exciting is happening. So this is actually step one. Step two is to construct the Hopf pairing between U tilde plus of Q, the so-called positive half, and U tilde Q minus of G with values in the ground field, which is always going to be C of 2 for me. And this pairing over here will pair EI with FJ. People usually normalize this differently, but let me call this, let me normalize it so that the pairing of EI with FJ is a Kronecker delta symbol delta IJ. Now already if you see me writing this and you know about Hopf algebras and quantum groups, something is wrong. The thing which is wrong is that this cannot be a Hopf pairing because these are not Hopf algebras. So let me tell you the second thing which I'm keeping under the rug in this talk. So whenever I will write Hopf and the star pairing, Hopf pairing, this means that one first enlarges the algebras in question. One first enlarges the algebras U tilde plus minus of G by adding the elements HI and imposing some straightforward relation. So by adding the elements HI, with a result being objects admitting a Hopf algebra structure. So the upshot of this thing over here is that this and this are not Hopf algebras per se, but if you enlarge them by adding the HIs and you impose some relations in a standard way, then you can make them into Hopf algebras, and then you can talk about the Hopf pairing between this Hopf algebra and this Hopf algebra. So what does Hopf pairing mean? It means that once you tell me what the pairing of EI and FJ is for all I and J, then the Hopf property of the pairing completely determines a pairing of anything from here with anything from here. because anything from here is a linear combination of products of EIs. Anything from here is a linear combination of products and FIs, and the Hopf property is telling you how to construct that pairing in terms of the pairings of individual EIs and FIs. So the point is, as opposed from a general bilinear pairing, which is a very general notion, there are not so many Hopf pairings, and actually there is only one of them up to scalar models. All right, that have a step 2. Step 3 now. Oh, actually, I could mention this now. Why do we care about a pairing? Well, if you have a pairing between two vector spaces, if it's non-degenerate, it might give you an isomorphism between one vector space and the dual of the other. If the pairing is Hopf, then it gives you a Hopf algebra isomorphism between one of these and the dual of the other. So it means that the pairing dualizes all of the Hopf properties of this with the Hopf properties of that. The algebra here becomes the co-algebra here, co-algebra becomes algebra, and the antipodes are switched in a certain sense. So that's why we care about this pairing being Hopf. But I said a magic word here, non-degenerate. You only get an isomorphism if your pairing is non-degenerate. If your pairing has a radical, then you're not going to get an isomorphism. And it actually turns out that this pairing over here does have a radical. So let's kill it. So let A plus be the radical of the pairing. So this is going to be the sub vector space of U2G plus be the radical of the pairing. So radical just means that K plus consists of all of those x's which pair trivially with everything. So I can squeeze my handwriting over there, but it's pretty clear what radical of the pairing has to be. Yes.
Sorry, can I ask what breaks the Hopf algebra structure of just this free associative algebra?
There's nothing wrong. You could define these as Hopf algebras. It's just that the Hopf pairing is going to have a kernel and a radical, and that radical will preclude you from saying that the dual of this is that, or it will preclude you from using the pairing to give you this identification. Well, but it would be for a second. So I'm just saying, take the radical of this pairing and kill it, and you will see that it's actually worthwhile. And well, therefore, step 4 is the last one. You define the quantum group. So you define UQ of G, the group that we actually wanted, as the free associative algebra generated by E's, H's, and F's, just like before. Modulo the relations in K plus, etc. So what does this mean? Well, K plus, remember, is a subspace of this. So the elements of K plus are going to be some sums of products of EIs. I'm just saying take those sums of products of EIs and kill them. And then do the same thing for the sums of products of FIs, and then you get your relations in the quantity. All right. At this stage, I can imagine, this is, it's all well and good in the abstract setting, but what does this actually mean for us in practice? I mean, after all, we knew that the Cartan algebra is generated by EIs, HIs, and FIs, modulo a concrete relation. And here I'm just saying, well, you take the algebra generated by EIs, HIs, and FIs, and you quotient by some kind of weird vector space, which is the radical of some Hopf pairing. Well, here comes a theorem, and this theorem is due to Glauber and Katz in the Lie algebra case, and I've seen it in Lustig's book in the cuneiform case. So the version over here is actually a Lustig's version, talking about the quantum group. What he proves is that for any Katz-Moody Lie algebra G, K plus, well, first of all, the fact that K plus is an ideal, it's a two-sided ideal. I've been calling it a vector space so far because it's the radical of the pairing. But because the pairing is a Hopf pairing, it's not hard to show that its radical is a two-sided ideal, which is a nice thing to have. K plus is an ideal generated by a single relation. And once I show you what this relation is that everything is going to make a little bit more sense. So this is generated by the following relation. Sum as K goes, that would be case. Let's do A, let's do B. B goes from 0 to 1 minus Aij, minus 1 to B, 1 minus Aij, choose B, 2 to the dii divided by 2, ei, the B, ej, ei 1 minus Aij minus B. So it's generated by this particular expression, and you might not have seen this, but the binomial coefficient over there is defined as follows. So it is n factorial underscore x, b factorial underscore x, n minus b factorial underscore x, where n factorial x is the product of m going from 1 to n, x to the m minus x to the minus m, x divided by x minus 1. So this is as long as a Q number. And the point is that when you send x to 1, or over here in this formula, you send Q to 1, n factorial sub x just goes to n factorial. And so this kind of x binomial coefficient, or the Q binomial coefficient over here, it just goes to the standard binomial coefficient. And so it's not actually hard to see that as you send Q to 1, this relation over here, namely the relation that you have to kill by killing K plus, is exactly equivalent to the iterated D bracket of EI to DJ being 0. So in other words, through purely abstract means, are wanting to get a Hopf algebra which is built out of a positive half and a negative half, and killing the radical so as to take a pairing which has a radical and making it non-degenerate, we actually got back the relation which is a natural Q deformation of the relation that we started from. And it actually turns out in a certain sense, by rewinding this argument, by looking at this argument backwards, that this particular Q deformation of this relation is the only one which preserves all of the structures which I want, Hopf algebra, the pairing, and so on. So this is the case, this is a setup for the quantum group associated with custom BMD algebra. I'm going to ask people if there are any questions, because after this I'm going to go on to loop the algebras. Yeah.
So the enlarging these guys to Hopf algebras, is that in a unique way or choosing some backwards?
Well, there's a reasonable way which deforms the Hopf algebra structure of the universal enveloping. The way you do is you throw in the HIs and you say that the co-product of EI, delta EI, is HI tensor EI plus EI tensor 1. And it's not the only choice. You could have also done HI to the 1/2 tensor EI plus EI tensor HI to 1/2, but this is like a standard way. And actually, you can apply some automorphisms, and any of these choices actually give you the same algebra structure. So to answer this question, I mean, in the grand scheme of things, there are probably many ways of adding the HIs, but there is a single one which is reasonable from the point of view of doing abstract representation theory on this, and having the HIs behave like some Cartan elements, the way they should. So yeah, this part has rely on some choices, but there's a standard choice.
So is it hard to see that this element is in the radical? Like, I'm wondering what the proof is for the, like, is it easy one direction or
anything else and get 0?
Yeah.
But it's just combinatorics, really.
Okay.
Because when you compute a pairing of this thing, the other product of EIs and EJs, well, you need to have the right number of EIs and of FIs and FJs for the cases, and then it's just combinatorics. It's some kind of Q binomial there. The challenging part is showing that everything in a radical is a multiple of this. So that's where the difficulty is. All right, so now I have told you about this part. I've told you about this part. I'm going to take a couple of minutes to tell you about this part, and then get to the fraction of this one. So what is the loop algebra? Well, this is not actually something that is not going to be so hard to define. The loop algebra of G as above is LG as a vector space, it's G polynomials, polynomials in a variable D, and the D bracket is essentially inherited from the D bracket of G. Well, should be a different kind of help. D bracket of X, Y, and here you put T to the K plus. So as a D algebra, everything is quite easy. This actually plays an important part in a number of parts of math. I probably should have said this about quantum groups. So UQ of G, maybe this is a nice part of, maybe this is a nice place to write this. So this appears in the theory of integrable systems. People who come to the seminar are probably, fans of this thing. Integral systems, they appear in the study of non-invariance. There's a beautiful picture over there. You can categorify these non-invariants. So quantum groups are connected to lots of things in math and especially in representation theory. If you're only interested in representation theory, they're nice because the representation theory of quantum groups mimics the one of Lie algebras quite closely. So that's why we like it sometimes. Group Lie algebras, these appear in conformal as building blocks in conformal field theory. You can build so-called vertex operator algebras from them. They appear in integrable system with a spectral parameter, and this was actually part of the motivation in studying the quantization, which I will show you in a second. Systems with spectral parameter, and I can imagine people in the seminar can find a lot more occurrences of these objects than I can in a couple of minutes. So this is what Hadoop the algebra is. Now what about the UQ of LG? How do we define the quantization of LG? So I'm going to put this as a question here. How to define UQ LG? Well, I'm going to say that we should actually just follow the four-step procedure over here and see what we get. But we're going to have to make some slight changes along the way because LG is a bit different from G. So the main change, I would say, appears in step one. So instead of defining the positive half as this thing like a free associative algebra and the negative half as a free associative algebra, we are already going to apply a relation when defining the thing with the half. So the thing with the half is going to be defined as the free associative algebra generated by symbols EI, D, where I goes over I and D goes over the integers. The intuition over here is that EID is like EI times e to the power D. So you kind of see how it's a generator of the corresponding units. But I want to apply to impose the relation even here. And the relation I want to impose is quadratic. And you will see in a second why I do so. So the relation which I impose is this. Here you see the Cartan matrix appearing. And on the right hand side, so this is for all I and j. I should probably write this down. All I and j and I. And I should tell you what EI of z means. EI of z is just the generating series as d goes from negative infinity to positive infinity of EI, d divided by z to the power. So the point is I take all of my generators and put them in a generating series. And this relation over here tells me how to commute two of these generating series. We'll turn this relation into an explicit quadratic relation among the EIDs, I fold it out, I equate the coefficients of E to something, W to something else, and I get some relations. Now you could ask, rightfully so, why do I impose this quadratic relation here? The answer is, it's because I impose this relation up here in the loop here. Indeed, as I take Q goes to 1, if I take Q goes to 1, this thing and this thing are just Z minus W, and then the relation I get is just that EI of Z, EJ of W, as a commutator of form of series times Z minus W is 0. And if you think about what this means, this is just saying, so this relation is equivalent to saying that the commutator of EID with EJK only depends on D plus K. It does not depend on the individual D and K. And this is entirely consistent with the rule over here, where the commutator of something times d to the k, something times d to the L only depends on k plus L. So this fact here is translated into this fact over here. Of course, you could ask, oh, why didn't I put q to the 150 here and negative 247 over there? But there's only so much I can hopefully ask you to take this on faith. Yeah.
Should I be concerned that these are unbounded series in both directions?
It's not a problem. So if you take the coefficient of z to the 0, w to 0, then a relation you get is finite. You get EI1, EJ0 minus another term is equal to a difference of two terms.
I see, but I shouldn't be sending W to Z.
Oh. It's an important of formal series,
Yeah.
and as long as you multiply it with polynomials in Z and W, you're okay. I think it's finite, but if you were to divide by Z minus W, then you'd be messed up. Okay, so this has just been a step one. I have justified for you the building blocks of this V algebra. So building blocks of the quantum loop. So that is step one, and maybe the thing that I didn't have a lot of room to write over there for step one is that you also sort of define UQ minus in the same way, but you use F's instead of E's. Well, whatever. This is becoming a motif of this talk. So define this analogously with F's instead of E's. Okay, so this has been step one. Step two, construct a Hopf pairing, and again with the same caveat as before, that for this to actually be a Hopf pairing, you have to enlarge these U's with tildes by adding some H's, and then they become Hopf algebras. And okay, I hope you can. Don't take me right out all the formulas right now because I won't have time to finish in like an hour from now, and I do want to finish in like 10 minutes or so. So you have a Hopf algebra, you have a Hopf pairing over here, and like that one was prescribed by saying what the pairing of EI with FJ. This one is prescribed by saying that the pairing of EID with FJK is the product delta of INJ and the product delta of D plus K and 0. So in other words, the pairing is non-zero only if I is equal to J and the integer indexes are opposites. But then everything else is as before. And then let J, as before, be the radicals. So J is mu q to the plus, be the radical. As before. Okay, and then step 4, as you can imagine, as before, you define your quantum loop group G as force of the quantum loop group generated by EID. The H's are also going to depend on the D, but I haven't written down the H's for you because, for lack of time. Modulo the quadratic relation. So we have already imposed this quadratic relation here. Let's call this quad. Relation quad. So I have to impose the quadratic relation. I have to impose the relations which are coming from J plus, and then I have to write the etc. because we also have permutation relations between E's, F's, and H's, which are pretty standard. But the important ones are going to be the commutation relations between the E's themselves. So we already know the commutation and relations in orange, the quadratic ones. The question now is, how do we understand the commutation relations which come from J plus? How do we understand J plus? Well, in the case which Greenfeld studied all those years ago, so he noted that when G is of finite type, when G is of finite type, the ideal J plus is generated by the following elements. And it's going to look a little bit maybe more messy, but it's actually not so much. So what you do is you write summation from B is equal to 0, 1 minus Aij, minus 1 to the B. And if you look at the formula in yellow on the top, you will see lots of parallels. In the Aij and here B, the same two binomial coefficient with BII divided by 2. But instead of a single EI, you're going to put a series of EIs. So I'm going to put here Z1, ZB. Here I'm going to put my EJ of W of another variable W. And here EI Z B plus 1. EI, the final Z is 1 minus Aij. And this has to be 0 for all I different functions. This is almost what I have to do to make this exactly true is to symmetrize with respect to the Z variables. All right, so this is a big extension. But the point is you take your individual EIs from this relation up here and you replace them by a series in its own variable, and then you have to sum over all of the permutations of Z1, Z2, dot, Z1 minus H. And the observation is that these things, the coefficients of these formal series are in the radical, and that the radical is generated by them. And this is true when G is of finite type. Actually, this also uses the work of other mathematicians to prove these assertions, but Greenfeld essentially built a piece for the first time to see all of these constructions based on these. And I think that this was one of the major motivations that he had, and he introduced YouTube. All right, so I want to take 5 more minutes to tell you, so is this the end of the story? Well, no. The point is, these relations are enough to generate a radical only when G is of finite type. When G is not of finite type, and G is of arbitrary Moody type, things are not that simple. And I want to tell you what you have to replace them with. The generality in which I will show the result is that of symmetric Moody type, which means that the Cartan matrix is symmetric. The philosophy actually carries through to the symmetrizable case, and the Cartan matrix isn't exactly symmetric, but I don't have a nice set of closed formulas in that case. I just have a heuristic about formula. So I'll just give you the symmetric case in which I understand everything that happens. So this is a theorem from a couple of months ago. So when G is of symmetric Moody type, so in other words, when G is the Moody Lie algebra associated with a symmetric Cartan matrix, the two-sided ideal, which we have to kill, the two-sided ideal of relations, that's the ideal J plus of relations, is generated by the following expressions. So here I'm going to have to draw a picture. First of all, I have to give you a relation for all I different from J and I. So far, I'm in the exact same kind of generality as the unknown relation here. I have to choose some non-negative integers K and L, whose sum is negative dij. So remember, dij, if I is different from j, is non-positive. Yes. So this one, this number is non-negative. And I also have to choose n greater than or equal to 1, so a natural number n. And associated to all of these data, I will give you a generator of j plus. Sadly, before I give you a generator, I have to draw a picture. So let me draw a picture. It's actually kind of a neat picture once you start knowing about these things. So these bullets on the top row and the bullets on the bottom row, you can think of them as the vertices in an oriented graph. And I will and all of the horizontal distances are going to be equal to 2. Now, just imagine that these are 2 copies of a horizontal axis, and this has length 2. Horizontal length 2. And now I'm going to draw these diagonal lines like this. Also oriented lines. Am I missing something? I think I'm missing something. Starting from here, going from here. No, this wrong. This is exactly what I was afraid of, that I would make a mess of the picture. You can probably fill in the picture by yourselves if I tell you what the convention is here. So the diagonal lines have horizontal coordinate bij. Meaning, whatever component has matter, but the vertices are spaced length 2 apart, and the pink lines have length dij. And I'm going to put some labels here on this. So I'm going to ask that there be x1, and this is xk plus 1, and this is xk plus n. And this is going to be y1, this is going to be yl plus 1, and this is going to be yl plus m. And then, in the middle, you have y2, So these indices over here are for indexing, and you can check that the condition over here ensures that this diagram is consistent. So you have an oriented graph with k plus m vertices on top and l plus m vertices on the bottom. And the relation which you associate to this is going to be summation over a certain combinatorial object, which I'm going to call S. And I will tell you what this is if there's time. Here you put a certain Laurent polynomial in the x variables, y1, yl plus m. And here I have to put a certain product of the series EIX1, EIXK plus m, and then with EJ1, EJY1, EJYL plus m. But the order of these things is indexed by S. So maybe I should just write over here what this S thing is. And then I can finish. So S and I'm sorry to go over, but I'll finish in 2 minutes.
You started late.
Well, I still finished after I was planning to, so it's worth finish quickly. So S is a certain type of subgraph of my picture over there, of this thing with green and pink, which has no oriented cycles, which has no directed cycles. And if you do have a subgraph which has co-directed cycles, then this normal ordered product just means the product where the variables are listed in descending order of the arrows. In S. So that,
Is it connected subgraph or?
no, it doesn't have to be, but in practice it's going to be connected. So what this means is that you choose an arbitrary total order of the variables x's and y's, which is compatible with the acyclic subgraph S, and then you write down the corresponding product in that order, and it's not going to depend on the order. And this P here is going to be some polynomial in the x's and the y's. The reason why I do have a formula for what this Cartan polynomial is, and it's not a bad formula, but the reason why I'm not writing it down is because you have the quadratic relation, you can always add multiples of the quadratic relation to any P relation, and then you get a relation which is equally good. There's no canonical way to write out this relation, because you're always doing things up to the quadratic relations that we had before. So this polynomial here, even though I have a formula for it, it's not a canonical formula in any way, so that's why I choose not to say. All right, so finally, a theorem is that these relations generate the two-sided ideal J plus, and the Greenfeld's old relation, the one from 35 years ago, relation, it's not exactly the same as this one, but it's equivalent to the case when k is 0, no, k is 1 minus no, k is equal to negative dij, and L is equal to 0, and then it's 1. But the point is that in general, you need more relations and not just his. You need these kinds of relations for all k and L. All right, that's my talk. Thank you very much.
Questions? Or from the Zoom audience, feel free to ask too.
Andrei, sorry, you mentioned something that this is extendable to the symmetrizable case.
Well, the philosophy is, but I don't have complete formulas. So I can tell you something extremely interesting, in my opinion, about the symmetrizable case. The interesting thing about these relations is that just like in the classical case, you only need to consider pairs of vertices. So it's like a rank 2 computation. You only have to consider I and J. But this is only true for symmetric Cartan matrices. I can show you a symmetrizable Cartan matrix where these kind of rank 2 relations are not enough, and you need a rank 3 relation.
Oh, wow.
The point is that if you choose your symmetrizable Cartan matrix a certain way, the combinatorics of a relation gets more and more complicated, and it's not such a straightforward rank 2 thing which only involves I and J. Actually, the Cartan matrix, the problematic Cartan matrix is this one. So this is the first example I know where you need a rank 3 relation which involves all 3 of the vertices.
Wow, I see.
But there is some philosophy as to how to get these relations in general. And if I have 1 more hour, I just explained it.
So, can I say that that's a little shocking to hear? I mean, shocking in a very interesting way, obviously. But I wonder whether this also has some ripple down effects. So does that affect the presentation of something you'd like, some kind of doubly affine break group you'd like to associate to your quantum loop?
Yeah, that would be nice, because this is how you understand the rank 2 relations in the usual quantum loop case. And I don't have an answer for this. I think it's a great question, and I think someone should look into it. But I haven't. And actually, unfortunately, from my point of view, lots of the lots of the algebraic research in quantum loop groups has been given in terms of their interpretation as quantum affine groups, which just means quantum groups for an affine Cartan matrix. But studying them from the perspective which I'm looking at them actually involves looking at their loop structure as like a feature in itself. And I haven't seen many of the standard features of quantum affine groups presented in this loop language, like in particular a generalization of a break group, which one I mentioned. And I think someone should look into that.
So for the finite type, your relation gives you Drinfeld's old one. Is that true for affine also? Like for some particular choice of KL?
The thing is, Drinfeld only wrote these things in finite type because he was interested in giving a new presentation of affine quantum groups. So the G is for finite type.
Okay, right.
The loops into G are another presentation of affine ones. To answer your question, it is believed to be true, even though I've never seen a proof that a Drinfeld relation over here is enough even if G is of affine type, except type A1 upper one. So affine SL2. So let's say. So that's the first case in which Drinfeld's relation isn't enough and you need one of these. And basically in this language is because the Cartan matrix in that case is 2, 2, and negative 2 and negative 2. A Drinfeld's relation is enough if all of the off-diagonal Cartan elements of the Cartan matrix are 0 or negative 1. In the cases of 0 and negative 1, my relation is equivalent to the old one. But as soon as the off-diagonal elements are negative 2, negative 3, and higher, you need these new relations. Otherwise, you're not generating the entire radical.
Andrei, is a kind of follow-up question. I'm still trying to digest what you said about the symmetrizable case, but not symmetric. So is this fact that you might need some rank 3 relations, does that only appear when you put a Q in, or would that also appear if you try to give a presentation of the loop algebra of a Kac-Moody algebra, which isn't affine, for example, or finite?
So, I'm not sure I heard the question, Valerio. Would you mind repeating?
Yeah, so I was asking whether this sort of potential rank 3 relation phenomenon, which you said can appear in the symmetrizable but not symmetric case. I was wondering whether that's specifically a Q fact, or whether it might also already appear if you try to present the loop algebra of a Kac-Moody algebra, which is neither finite nor affine, and isn't simply laced.
So I'm not sure I understand the question, but Valerio had some qualities probably. So this Cartan matrix here is an algebra which is neither of finite type nor of affine type. It's not symmetric, but it is symmetrizable. And what I'm saying is that for its UQ of LG, you need these higher.
No, I understand that part. So maybe something got lost on Zoom. So no, I understood that part. What I'm asking is that if I took exactly this matrix,
yeah,
right, I try to take and I take the loop algebra of the corresponding Kac-Moody algebra.
Yes.
But somehow, if I were content to take Q is equal to 1, so if I didn't care about the quantum.
That's a.
Would I still stumble into those rank 3 relations, or are they something purely a product of Q?
Purely a product of Q.
Of Q not being equal to 1.
The relations over here, they go to 0 as you take Q to 1. Unfortunately. So another question which I would like someone to address at some point is there like an integral version of these relations which works over Z double brackets Q instead of over rational functions in Q. The task being to modify these relations somehow in such a way that they survive the generation to Q goes to 1. These relations over here, they go to 0 when you send Q to 1. So because of that, my relations actually require the fact that Q is not a root of unity. So unfortunately, understanding the answer to your question, to understand the answer of your question, one would have to understand the integral form of these quantum loop groups, and that is still up in here. But to be honest, I actually expect the integral form to be even more complicated and to require even more complicated relations. even though this expectation is just a heuristic right now, it doesn't follow from what I just said. I would be extremely surprised if in the integral form you could get away with just a standard relation, but not in the rational form of the quantum.
Any final questions?
Is it easy to draw an example of this graph in some simple case?
Yeah, I kind of should have, right? Here's a simplest case. So if you take this matrix 2, -2, -2, 2, then the graph just looks like this. I was getting a little bit too ambitious. Bam, 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 bam. And in this case, you just have a cycle of length 4, and there are 4 ways to remove edges in such a way as to break the core-oriented cycles, because there's only one oriented cycle. And in this sum, there are 4 terms. One of them has, you should have given this, but they're much more visible than what I wrote over there. So in one of the terms, the order of the variables is x1, x2, y1, y2, then x2, y1, y2, x1, and then you see all of the cyclic permutations. And in that case, even the polynomial is like super simple. I have to break it down. But in the general case, you do have that more complicated graph. You need to take all k, l, and m. So this is a particular instance of n is equal to 1, and it kind of gets more complicated.
Okay, thank you,
Thank you
Andrei.
so much.
We'll-